In this lesson, we'll take a look at the dot product, which is loosely kind of a way of multiplying vectors. And we're going to start with an example, then we'll talk more about the dot product starting on the next page. Work is defined as the product of a displacement and the magnitude of the applied force in the direction of motion. And in this first example, we have an object that's going to be moved with a 200 Newton force, a distance of 50 meters. So the distance is 50 meters along here, but the force is not acting in the exact direction the object's moving. It's acting at an angle of 15 degrees with the horizontal. Like for example, if you were pulling something along the ground with a rope attached to it, or maybe pulling a wagon along, and the handle is of course not in the exact direction you're going, but it's at an angle. I mean, unless you want to get down and crawl along the ground and pull exactly in the same direction as you're going. So that's why the angle of the applied force is not the same as the direction the object's actually moving. Now, the amount of work done, what we need to do is calculate the applied force in this direction. So it's actually just a horizontal component of that 200 Newton force at that angle. And so we would calculate the size of that by taking the 200 newtons and multiplying it by the cosine. Remember, the length of the vector times the cos of the angle is the size of the horizontal component. And so 200 cos 15 is 193.2 newtons. So that's the magnitude of the applied force in the direction the object's moving. So it's the same amount of work would be done if instead of pulling at 200 newtons along that, if you pulled in the direction the object's moving it with 193.2 newtons. Now the work is the applied force times the distance the displacement the object moves. So we would take the net force, the 193.2, and multiply it by the displacement, the 50 meters. And so that gives us 9,660, and the units would actually be newtons because the forces are applied, the units are in newtons, and the displacement is, the units are meters. So the units for work then would be Newton meters. There are other units for work, but we'll just leave them in terms of the units of these two quantities. Now, this is really a dot product quantity, and I'm going to start talking on the next page about what the dot product is. There's actually two different formulas or ways of calculating the dot product, and we'll start with this one, and that's the symbol for dot product right there. It looks like a big dot between the two vectors you're taking the dot product of. So one way to calculate the dot product is it's the product of the two magnitudes. So we take the magnitude of A and the magnitude of B, or the length of A times the length of B, multiplied by the cosine of the angle between the two vectors. And the angle is defined to be, if you place the two vectors tail to tail, it's the angle between them. I guess if you place them head to head, it would be the same angle. Now, theta is always defined to be an angle between 0 and 180. So you never have a reflex angle for theta. It's always defined to be the angle between an angle between 0 and 180 degrees. In this next example, we're going to calculate the dot product. We're given the magnitude of each vector and the angle between them. So for the first one here, we will go 8.5 times 6 times the cos of 38 degrees. And if you take your scientific calculator, that works out to just be over 40. In the second one, the magnitudes are 7 and 12, and the angle is 90 degrees. So we go 12 times 7 times the cos of 90. Well, the cos of 90 is 0, so 12 times 7 times 0, of course, is 0. The last one, notice that the angle is bigger than 90, it's 150 degrees, so we would go 2 root 7 times 10 times the cos of 150. And the cos of 150 is a negative value, that's why this works out to be a negative dot product. It's about negative almost 46. Now, I did three different dot products here. I got a positive value, a negative value, and 0. And so that's kind of three different classifications for the dot product. Notice for the dot product values that if the angle is between 0 and 90, or an acute angle, the dot product will always work out to be a positive value, greater than 0. If the dot product is 0, that means that the angle between them must be a right angle, or 90 degrees. And the last one over here, the dot product is negative, less than 0, if the angle is between between 90 and 180, if it's an obtuse angle. Some properties of the dot product. A dot B is the same as B dot A. That's called the commutative law. It doesn't matter what order you take the dot product, you always get the same quantity. That is not the same with every possible mathematical structure. There are things, and when we, if you look at the cross product lesson, another lesson in this series, you'll see that the commutative law doesn't hold for cross product. But we'll save that for another time. A dot B plus C, this is the distributive law. If we take the dot product of A with a sum of B and C, we get A dot B, we distribute it in, so A dot B plus A dot C. So that's the distributive law. A dot B plus C is A dot B plus A dot C. If you take a dot product of a vector with itself, A dot A, it's the same as the magnitude of the vector squared. If you take the dot product of A with the 0 vector, you get 0, and that's because all the components of 0 vector are 0. If you take the dot product of A with U, where U is a unit vector in the same direction as A, you actually get the length of A. That's the scalar it works out to be. Notice that in all those examples on the previous page, the dot product gave you a scalar value. The dot product isn't a dot product. It's just a number. If A dot B is equal to 0, again, there's a scalar, then that means that the angle between the two vectors must be a right angle, or 90 degrees. That's the only way you get a dot product of 0. In this example, we're asked to expand and simplify the following, take the dot product of these two vectors' sum and differences. And so we would go 3w dot 2w, so that's the first thing I'd write down. And this is really like FOIL, or multiplying two binomials together. And then we go, after we did this, we would go 3w dot the negative 4u, so that's this one here. U dot 2w would be the next one, and then u dot negative 4w, so negative u dot 4w, 4u, sorry. Now, we can simplify this a bit. 3 times 2 is 6, so that's 6w dot w. Negative 1 times 4 is negative 4, u dot u. And in the middle, negative 3 times 4 is negative 12, 1 times 2 is 2. Both of these would be a u dot w, u dot w. I'm just writing them in the same order. They're not written in the same order here, but I changed it so they are written in the same order, so we can see more easily that those are actually like expressions. Now, w dot w is the length of w squared, so that's a simpler way you can write that. These are like terms, so I can combine those to get negative 10 u dot w, and of course u dot u is the same as the length of u squared. Now what we're going to develop on this page is another formula for calculating the dot product, which will be very useful and be used more than the original definition that you got on the top of the second page. And although this is going to actually get long at times, it will simplify a lot at the end. So we have these two vectors A and B here, and the so A is defined to be the vector A1 comma A2, and B is the vector B1 comma B2. That's just their x and y components. Now the length of A, remember the length of A is you take the two components, square them and add them, so it's the x component squared plus the y component squared. Same for B. Now, in the diagram, vector C is vector A minus B. If you use the triangle law here, notice that if we take this vector right here, B, and it and C are placed tail to tail, plus C is equal to this vector A. So if I rearrange this by subtracting B from both sides, I get C is equal to A minus B. So vector C is vector A minus vector B. So we can substitute, in order to find the components of C, we can substitute the components of A and B in. So remember, this is vector A, this is vector B. We're subtracting them. Subtract the like components. So A1 minus B1 is the x component, A2 minus B2 is the y component. If I want to then find how long this vector would be, its magnitude, the magnitude of C squared would be this squared plus this squared, which is what's written here. Now if we expand this out, and I'm just expanding the squares, so for example, if I'm doing I'll do this one here, A1 minus B1 squared is A1 minus B1 times another A1 minus B1. So we're just expanding this out, so A1 times A1 is this A1 squared here. and then a1 times the negative b1 would be minus a1 b1. This product is the same thing, a1 b1, and this product would be plus b1 squared. So there's the b1 squared, there's the a1 squared, and these two terms combine to give you negative 2 a1 b1. And the same thing, this expands out to these three terms in the end. So that's where all those 6 terms come from. Now, using the cosine law, we could also find how long that vector is in terms of theta and the length of A and length of B. Remember, in a triangle, if you have two sides and the angle between them, you can use the cosine law to find out how long the third side is. So in order to find the length of vector C, it would be the length of A squared plus the length of B squared minus twice A times the magnitude of B times the cosine of theta. I said twice A, it's actually the magnitude of A. Now, in both cases, we have magnitude of C squared equals. So this whole quantity here should equal this whole quantity here. So we're going to equate them. This is equal to this one here. Now, in place of the magnitude of A, I'm putting A1 squared plus A2 squared. In place of the magnitude of B, it's B1 squared plus B2 squared. So I made that substitution. Now notice that there are several things the same on both sides. Magnitude of A squared and magnitude of A1 squared, not magnitude of A, A1 squared, and then a B1 squareds, and then the A2 squareds are the same, and the B2 squareds are the same. So they'll just all subtract out or cancel out. Some people use the term cancel out. So all we actually have left is this. This quantity is the only thing left on the right side. And what we have on the left is negative 2a1 minus 2a2, negative 2a1b1 and minus 2a2b2. And if we were to divide everything by negative 2, we would end up, both sides, we would end up with a1b1 plus a2b2 equals, and if we divide with negative 2 here, then that's gone, magnitude of A, magnitude of B, cos theta. Now remember, from the top of the second page, that's the dot product. So this quantity right here is also the dot product. So this is actually the another way to calculate the dot product. So another way to calculate the dot product is actually just multiply the two x components together plus the product of the two y components. So that's a different way of calculating the dot product. You see, the thing is, often you won't have the angle between the two vectors, so that's why this is a convenient formula to use. So there's the second formula for calculating the dot product, and specifically of Cartesian vectors, where we of course have the components. So in example number 4 here, we're going to calculate the dot product of A and B. So we have to read the components. So A is the vector 2, 5, and B is the vector 3, 1. So we would go 2 times 3 plus 5 times 1. So 6 plus 5, of course, is 11. So the dot product of A and B is 11. For the second one, D is the vector negative 2, 5, and H is the vector 4, negative 1. So we go negative 2 times 4 plus 5 times negative 1. So negative 8, negative 5 is negative 13.